Batteries, they're everywhere, right? Powering literally everything from our phones to our cars. And for what, decades now, lithium-ion has been the undisputed king. But, the race is always on for something better, something cheaper, more sustainable. So yeah, let's dive into the hunt for the next big thing in energy storage.
But here's a thought. What if the next huge breakthrough isn't going to be found in a lab with bubbling beakers? What if it's discovered inside a supercomputer? We're going to look at how scientists are using these incredible new tools to peer right inside a battery, down to the atomic level. And trust me, it is changing everything. Okay, so let's get down to it. Here's the core of the problem, the big conundrum. We're completely hooked on lithium-ion batteries. They're great, they're powerful, no doubt. But lithium, it's expensive, and there's only so much of it to go around. This has sent researchers scrambling for a better alternative. And you know what? It's led them to an element that is super, super common.
And that element is sodium. Yep, if you look at the periodic table, it's right there in the same group as lithium. And it's ridiculously abundant and cheap. I mean, just think about table salt. But of course, there's always a catch, right? Sodium ions are just bigger. They're beefier than lithium ions, which makes them kind of clunky and a lot further to move around inside the battery. And historically, that's meant less power, less capacity. So this really sets sodium up as the perfect underdog, The potential is just massive. If, and that's a huge if, scientists can figure out how to squeeze more juice out of it. And this right here is where our little scientific detective story really kicks off. So the big question is, how do you get more power? Well, the latest thinking is that we need to go beyond just the usual way of doing things. In a typical battery, you've got these metal atoms in the cathode, and they're doing all the heavy lifting, right? They're storing and releasing the energy. But what if you could get the oxygen atoms to pitch in too? If you could do that, you would dramatically, and I mean dramatically, increase the battery's capacity. Okay, but getting oxygen to play along, that's a really high-stakes gamble. It's a classic double-edged sword. On one hand, yeah, it can unlock a ton of energy. But on the other, forcing oxygen to do all this extra work can make the whole structure of the battery unstable. We're talking rapid degradation. Or worse, it could start releasing oxygen gas, which is, not good at all. All right, before we dive any deeper, let's just do a quick refresher on the basic engine of a battery. It's called the redox reaction. All that really means is it's the process where atoms give and take electrons. Super simple. And that exchange, that little dance of electrons, is what stores and releases energy. The key question, though, is which atoms are doing the dancing? And that brings us to the two main players here. The traditional way is something called cationic redox. This is where the metal ions, the cations, do all the work. It's stable, it's reliable. Think of it like the super strong steel frame of a skyscraper. Then you have the new high-power approach, anionic redox. This is where we try to get the oxygen ions involved. It offers way more power, but it's like trying to use the building's concrete walls to hold up more weight. It might work, but you're seriously risking a catastrophic collapse. So to figure out how to get all that power without the risk of collapse, a team of scientists in India basically decided to ditch the traditional lab bench. Instead, they built a virtual one. They used AI and some incredibly powerful simulations to see what's actually happening at a level of detail that was, pretty much impossible before. And this is where it gets really cool. It's not possible to simulate every single way atoms could arrange themselves. It would take forever. So what did they do? They used AI as a kind of super fast filter. They generated hundreds of potential atomic structures and then just let the AI models rip through them, sorting and sifting to find the most stable, most promising candidates. It's like finding the needles in an atomic haystack, but with a giant AI magnet. So they have this really clever three-step workflow. Step 1, generate a massive pool of possibilities. Step 2, unleash these specialized AI models to just tear through them at lightning speed. And then, step 3, they take only the absolute best candidates and run them through a super, super detailed simulation. You can think of it like an incredibly powerful atomic calculator that gives them the final precise answer. It's just a brilliant way to focus all that computing power exactly where you need it. Now, the specific suspect they put under this virtual microscope is a sodium-rich material called sodium ruthenate. The thing about this material is that it was known to perform surprisingly well, but nobody was quite sure why. Was it somehow taming that risky oxygen reaction, or was something else entirely going on? And here
Here's where our detective story takes a really interesting twist. After running their best candidates through those heavy-duty simulations, the virtual lab started spitting out data. And the results, they were not what most people in this field would have expected at all. So what did these incredible tools actually find? How does this stuff really work, down at the atomic level? Well, let's take a look at the evidence they uncovered.
Okay, and this right here just brilliantly shows how powerful their method is. The black line on this graph, that's data from a real-world physical experiment. The other colored lines, those are the predictions from their virtual lab. Now, zero in on those yellow diamonds. That's the result from their absolute best, most accurate simulation. I mean, look at it. It matches the real-world data almost perfectly. This is the proof their virtual microscope is seeing reality.
And now for the big reveal. This shows us exactly which atoms are doing the work. You see those big red peaks? That's the metal, ruthenium. And the little blue peaks? That's the oxygen. So completely contrary to what a lot of people might have guessed for a material so rich in sodium, it turns out the metal, the ruthenium, is the absolute star of the show. That stable, reliable cationic redox reaction, it's overwhelmingly dominant.
You know, the researchers themselves put it perfectly in their paper. They prove that the secret to this material's success isn't some magic trick to tame the risky oxygen reaction. Nope, it's much simpler. The metal itself is just a powerful, stable workhorse, all thanks to its super strong bond with oxygen. So, okay, what does all this mean for the future of batteries? Well, it basically hands us a completely new roadmap for how to design the next generation of energy storage. Okay, let's break down why this is such a big deal. First, it solves the mystery, right? We now know this material is stable because of its strong metal framework, not because of some risky oxygen chemistry. Second, it gives battery designers a whole new playbook. It says, hey, go find more metals that can be these stable workhorses. And finally, and this might be the biggest deal of all, it's just powerful proof that these AI-driven computational methods can massively speed up the discovery of new materials. It really changes how science itself gets done. And that leaves us with a pretty fascinating question to think about, doesn't it? We've always had this picture of scientific breakthroughs happening in labs, with test tubes and chemicals. But this research, it suggests the next great leap forward in battery tech might not be mixed in a beaker at all, but discovered atom by atom inside a computer.